We're going to do a little bit more today with Taylor series. Remember, one of the things that we started with, one of the things you have to be able to recognize quickly when you see it, are the easy problems, the ones where you don't have to do a whole lot of work because it is an infinite geometric series just staring at you in the face. This equation, g of x equals 1 over x, 1 plus x cubed, is in the form of the infinite sum of a geometric series. a1 over 1 minus r. So what we need to do is just identify, the a1 is 1, and the r is negative x cubed. Make sure you're careful about that negative. We're supposed to see a negative, a minus r. So if we see a plus sign there, just remember that means your r is negative. And then we can write this as the sum of 1. So this is g of x. It's 1 plus 1 times r plus 1 times r squared. And since we're squaring that negative x cubed, it's going to become positive. Plus 1 times r to the third, and so on. And if we were to write this as a general term, we can see that, first of all, the signs are alternating. And the common ratio we keep multiplying by is x to the third. Now, I don't need to put the negative in here also because I've already taken care of that with the alternating negative 1 to the nth there. So I can write this as the sum from n equals 0 to infinity of negative 1 to the nth times x cubed to the nth. And that's an infinite geometric series. The reason I wanted to go over that is because we will use that in our next example. We're going to find the last of the basic Taylor series to know. I put that in quotes there, basic, because it's not that common. It's not the most important thing in the world, but it's cool the way it works, so we're going to do it anyway. Remember the idea behind finding the Taylor series, the way we did it for e and e to the x and sine of x and cosine of x and ln of x, same thing we did for all of them, was to equate derivatives. Well, that's how we're going to start. We're going to start with the derivative of f, so f prime of x. And arctangent of x, we don't use it very often, but we learned it. We know what the derivative is. It's 1 over 1 plus x squared. And you might look at that and say, wait, so now I have to find f double prime and f triple prime and equate the derivatives and find the coefficients and then find a pattern in them, and that seems kind of annoying. And you're right, that would seem kind of annoying. But hopefully what you're seeing is when you're looking at that 1 plus over 1 plus x squared, you say, wait a minute, didn't we just do that? Isn't that an infinite geometric series? With an a1 of 1 and an r of negative x squared. So can't we just say that f prime of x is equal to the infinite sum of 1 minus x squared plus x to the fourth minus x to the sixth, etc., etc., etc. Just matching exactly what we did in the last problem, except this time the r is x squared instead of x to the third. So our r will be x squared to the n, or x to the 2n instead. And you might be saying, wait, we weren't trying to find f prime of x. We wanted a Taylor series. And by the way, I should point out that what we're finding is the Maclaurin series. We didn't want the Maclaurin series for f prime of x. We wanted it for f of x. But we have a way to go from f prime of x to f of x. We've been doing it all year long. F of x is the antiderivative of f prime of x in respect to x. So what we can do is just take the antiderivative of all of those terms. The antiderivative of 1 minus the antiderivative of x squared plus the antiderivative of x to the fifth. Sorry, antiderivative of x to the fourth is x to the fifth over 5, minus the antiderivative of x to the sixth. And hopefully you're seeing the pattern here. We are still alternating signs, so that's not going to change. But now our exponent on the x isn't 2n, it's 2n plus 1 because we used the power rule. So every time we had an exponent of 2n, we had to add 1 to it. But because of the power rule, we also have to keep putting the denominator to match that new exponent, 2n plus 1. So that means that f of x, our arctangent of x, is equal to that infinite sum. So the infinite sum, we're starting when n is 0, because that way we'll start with negative 1 to the 0 power. We'll start with a positive. Negative 1 to the nth times x to the 2n plus 1 over 2n plus 1, which, if you write out the first few terms, you can see the pattern pretty clearly. It's alternating signs, and both exponents and denominators are simply just odd numbers. Notice how there's no factorials involved here, unlike the e and the sine and the cosine. It's more like the ln of x, where our denominators are just plain numbers. But unlike the ln of x, it's only the odd numbers. There is a catch to this one. We do have to be careful about this. Kind of skip this in the last example. But remember, whenever we do a geometric series, that a1 over 1 minus r, that's only true if the absolute value of the r is less than 1. So all of this is only true when our original r of x squared is less than 1. Which means that x squared itself has to be between negative 1 and 1. Well, x squared can never be less than 0 anyway, so it doesn't really matter for us. But we do need to make sure that x is between negative 1 and 1, so that way when we square it, it is still, when we square it to get the r, the common ratio, it's still less than 1. This, by the way, is called the open interval of convergence. We'll talk more about this next lesson, but I'll give you the name now. And what we're saying when we use the open interval of convergence is that as long as x is between negative 1 and 1, we can use this power series as a way to evaluate the arctangent of any number. Now, if we want to evaluate the arctangent of a number that is not between negative 1 and 1, we would just have to, like we saw last lesson, we would just have to figure this whole thing out again with a different, centered on a different x value, which we're not going to do right now. Worth pointing out, there's another term here. It's called the radius of convergence. If we think of the interval of convergence as almost like, well, it is a range of values, the radius of convergence is half of that range. So this is the radius of convergence, going from where we're centered, which is 0, to the edge of the interval of convergence. This radius of convergence is also 1. So the interval of convergence we would have to write as an interval. The interval of convergence is from negative 1 to 1. The radius of convergence is a number.